Module 2, Lesson 18, Least Common Multiple and Greatest Common Factor. I'll say straight up I've made quite a few modifications to this lesson, trying to provide a little bit more clarity between the difference, trying to make more clear the difference between greatest common factor, least common multiple, and using some strategies that I prefer over what was included in the materials. So if you're trying to find a step-by-step walkthrough for exactly what's in the Engage New York Eureka Math materials, this isn't a perfect step-by-step, but this is how I teach this in my classroom. All right, so I can find the greatest common factor of numbers 1 through 100, and I can find the least common multiple of numbers 1 through 100. So it's really important to think about the definitions of these words. The greatest common factor of two whole numbers is the greatest whole number that is a factor of each number. The greatest common factor of two whole numbers, A and B, is denoted, we would say GCF, and then we would have A and B, and we would write it out that way. And we'll see what that looks like in a few minutes. All right, so taking a look here at example 1, finding the greatest common factor of 12 and 18. Now, in the materials, it would have you find the factor pairs that lead to 12 and 18, lead to the finding all the factors of 12 and 18. My experience has been that this becomes a guess and check method, especially as we start to move towards larger numbers within 100. Students don't know all of the multiplication facts that lead to getting some of these numbers, so we need to apply a greater level of mathematical thinking. We need to have some other strategies in place. So one of my favorites is to use the upside down cake, which is linked to in the notes at the start of the slide presentation for this. And it's simply what can I divide these numbers by? Well, I see both of them are even, so I can divide them by 2. And so this is called factoring. I am going to divide a 2 out. 12 divided by 2 is 6, and 18 divided by 2 is 9. So 2 is a common factor of 12 and 18. And then I look at 6 and 9 and say, hey, I can divide both of those by 3, so I will factor a 3 out. Factoring out a 3 means I will divide a 3 out. 6 divided by 3 is 2, and 9 divided by 3 is 3. Now, the things that I have divided out of both of the numbers, I can multiply those together, and I will have a greatest common factor of 6. GCF of 12 and 18 equals 6. So what we're looking for here is the greatest number that I can divide both terms by, both numbers. And the approach that I am taking is looking for what can I divide. Now in the lesson materials, they would tell you to find the factor pairs, 1 times 12, 2 times 6, 3 times 4. And for 18, you'd have 1 times 18, and 2 times 9, and 3 times 6. And you would look for the largest number that is on both of the lists. Now, you could also look for, if you are just looking for common factors, these are all numbers that are on both lists. But I would like to point out that all of those were also found on the upside down cake. 12 and 18. I can divide them both by 1, and I have 12 and 18. I can divide them both by 2, and I have 6 and 9. And I can divide them both by 3, and I will have 2 and 3. So You'll remember we had 1, 2, and 3, and then we also had 6 were the common factors of 12 and 18. And 6 is the greatest of these common factors. A second strategy that I like to introduce students to is prime factorization. So I take the 12, and prime factorization, you frequently see it as factor trees. And you keep breaking the factors down until you have prime factors. So at the end of the roots of the tree, at the bottom of the tree, we have a prime factorization of 2 times 2 times 3. And for 18, we have 2 times 9, 3 times 3, and we have 2 times 3 times 3. And what you do now is a comparison between the prime factorizations. If you're looking for the greatest common factor, we are going to compare these prime factorizations with each other. And when I do that, I have a tendency to line things up. So I see I've got a pair of 2's and I've got a pair of 3's. So the common factors are the 2 and the 3 for a greatest common factor of 6. So a couple of different approaches for finding a greatest common factor. All right, taking a look here, activity 1, we're just going to find some greatest common factors of numbers. In class, I would have students working with a partner as they did these, rather than some of the other activities that are outlined. And you'll remember that I'm doing this out of order. In the lesson materials, they would go to example 2 and finding least common multiple, but I want to get solid greatest common factor before we move to least common multiple. And in class, these would be set up as stations, and I will probably have it just be a partner activity. All right, so the greatest common factor of 30 and 50. And I can see that both of these can be divided by 10. They both have a 0 in the ones place. And 3 and 5 are both prime numbers, so the greatest common factor is 10. 30 and 45. I know that these are both multiples of 5 because we have a 0 in the ones place and a 5 in the ones place, so I can divide out of 5. 30 divided by 5 is 6, and 45 divided by 5 is 9. And these are both multiples of 3, so I can divide the 3 out. And I have a greatest common factor of 15. All right, 45 and 60. Now I can't help but notice that 60 is double the 30, so I'm guessing that this 15 is going to come into play someplace. Because here we had 30 and 45, and now we have just doubled one of the numbers. So in my head, I'm thinking maybe what I've got here is a double thing, but we'll see. This is where we play with math. 45 and 60, and I can divide both of those by 5, and I get 9 and 12, and I can divide 9 and 12, both of them by 3, and I get 3 and 4, and I see that I still have 15. So even though I have noticed that there is a doubling going on with the 30, there was not a doubling going on with the 45. So the doubling is an interesting observation, but it doesn't mean that my greatest common factor has been doubled, because I did not scale both of the terms times 2. All right, 42 and 70. And I think these are both multiples of 7, so I can divide out of 7, and I get 6, and I get 10. And I can divide both of those by 2, and I get 3 and 5. 3 and 5 are both prime, so nothing else in common. I've got 7 and 2 for a greatest common factor of 14. All right, 96 and 144. Well, these are both even numbers, so I can divide them by 2. 48 and 72. And I think I can divide both of those by 2, 24 and 36. And I think those are both multiples of 4. 24 divided by 4 is 6, and 36 divided by 4 is 9. And those are both divisible by 3. And that leaves me with 2 and 3. So I've got 2 times 2 is 4, times 4 is 16, and 16 times 3 is 48. 96 divided by 2 gives me 48, and 144 divided by 3 would give me 48. So 48 is the greatest common factor of both of these. All right, and now we just go through some problem-solving activities. There are 18 girls and 24 boys who want to participate in a trivia challenge. If each team must have the same ratio of girls and boys, what is the greatest number of teams that can enter? So we're using our scaling here to help us to figure out teams. So I've got 18 girls and I've got 24 boys, and I want to scale this to find the greatest number of teams. So we'll use the greatest common factor for this. So we will divide out, well, these are both divisible by 2, 9 and 12, and those can both be divided by 3, which leaves me 3 and 4. And I see that we have 6 teams. Now, there are a couple of things to explore, to look at as we think about this. It's great that I found the greatest common factor, but let's look and see how this applies in the problem here. So I need to have teams, and I need to be able to total up to 18 girls and 24 boys. And I need to have the same ratio of girls and boys. Now, right down here at the bottom, I have a ratio value of 3 to 4, which is a total of 7 teams. So I've got the girls, I've got the boys, and I've got the total number of students that are playing on the team. If I say that I'm going to make 6 teams, I scale this up by 6, and I have 18 girls that are participating. And I scale this up times 6, and I have 24 boys who are participating. And I scale this up by 6, and I have 42 students who are participating. So the 6 is the greatest common factor. Down here at the bottom, I have my ratio, girls to boys, which helps me find out how many students are on each team. So as we start taking these numbers apart, we start to have a lot of power. Let's look at another one. Ski club members who are preparing identical welcome kits for new skiers. The ski club has 60 hand warmer packets and 48 foot warmer packets. Find the greatest number of identical kits they can prepare using all of the hand warmer and foot warmer packets. How many hand warmer packets and foot warmer packets would each welcome kit have? So we've got a total of 60 and 48, which means we have a ratio of 60 to 48. If we can find the ratio value here, we can find out how many to put in each of the kits. And we can also then figure out how many kits we can make. So I'm going to take this ratio here and I'm going to scale it down. Scale it down using the greatest common factor. Well, these are both divisible by 12. Very nice. 5 and 4. So I can see that my ratio value here, if I'm setting this up on a table, I've got 5 of the hand warmers, I've got 4 of the foot warmers, the foot warmers. In each packet, I will have a total of 9 items. If I scale these all up by 12, 9 times 12 is 108. 60 plus 48 is 108. I can see that in each of my packets, I will have 5 hand warmers, 4 foot warmers, and a total of 9 warmers. And if I were to scale this up using up all of my materials, I would have a total of 12 kits. All right, there are 435 representatives and 100 senators serving in the United States Congress. How many identical groups with the same number of representatives and senators could be formed from all of Congress if we want the largest group possible? How many representatives and senators would be in each group? So once again, I've got this ratio going on here, 435 to 100, and I would like to find, in some ways, the ratio value here. I'd like to make the largest possible groups out of this, which means I'm looking for a greatest common factor. Now, I can see that both of these can be divided by 5, which will give me a 20 here, and 435 divided by 5. I've got 87. Now, this is where it starts to get a little bit tricky. 87 and 20. What do they have in common? Well, let's run through some of our divisibility rules real fast. They are not both divisible by 2. I can't divide them both by 3. 87 would divide very nicely by 3. 8 plus 7 is 15, and 15 can divide it by 3. But 20 does not divide by 3. 87 is an odd number. It is not going to divide by 4. I know that they are not going to divide by 5. I can't divide by 6 because they are not divisible by 2 and by 3. 7, we don't have a divisibility rule for that we have explored. Let's take a look at 8 here. Well, I know 20 doesn't divide by 8, so that's not going to work. And I know that 20 doesn't divide by 9. So at this point, the only possibility that I might have would be a 7, but I know that 20 doesn't divide by 7. So running through my divisibility rules here, I think I've gone as far as I can. I think I've done everything I can with this problem. I think that we would make 5 groups, and I think we would have 87 representatives in each group, and I think we would have 20 senators in each group. All right, is the greatest common factor of a pair of numbers ever equal to one of the numbers? Explain with an example. So I've got number A and I've got number B, and I am looking for the greatest common factor. Is the greatest common factor ever A or B? So pause and think about that for a moment. And the answer is yes. For example, just a nice easy one here. If my numbers are 2 and 4, the greatest common factor of 2 and 4 is 2. So it is absolutely positively possible that A or B is the greatest common factor. So we should always keep our eyes open for that. Is the greatest common factor ever greater than both numbers? And pause and think about that for a moment. And I hope you came to the conclusion that no, that isn't possible, because factors are always less than the number. If I'm looking for the factors of 100, the factors are always less than, and I need to say this more clearly, less than or equal to 100. Factors, by their very definition, are less than or equal to the number. So the greatest common factor cannot be greater than both of the numbers. All right, the other half of the lesson, looking at least common multiple. The least common multiple of 2 whole numbers is the smallest whole number greater than 0 that is a multiple of each number. A multiple is a more than one of a number. The least common multiple of 2 whole numbers, A and B, is denoted by LCM A and B. So this is how we get the instruction to find the least common multiple of A and B. All right, so looking at an example here, finding the least common multiple of 12 and 18. Now, one very common strategy is to just start listing multiples. 12, 24, 36, 48, 60, 72, and we keep going. And then we come down to 18 and we list its multiples: 18, 36, 36 and 18 is 54, and 54 and 18 is 72, and 72 and 18 makes 90. So we've listed off a few multiples, and now we go back and we start asking ourselves, what is the lowest number that is on both of the lists? And we see that that is 72. So one very common strategy is just to list the multiples and look for what they have in common. However, I am a huge fan of going back to prime factorization and using prime factorization to help do this. So 12 and 18. I'll do this one with factor trees first, and then we'll play with the upside down cake. 12 and 18. So a number that I can divide both of them by is 2, which would give me 6 and 9. And I can divide them both by 3, which gives me 2 and 3. So what they have in common is 2 times 3. So 6 is a common factor. The 2 and the 3 down here are things that they don't have common, but things that I have to consider as I find least common multiple. And I was going to do factor trees, and here I am doing upside down cake again. That's okay. So I can do 6 times 2 times 3. So I take the 2 times 3 and I combine that to make the 6. And then I will take the items that are different, the 2 and the 3, multiply this all together. 6 times 2 times 3, 12 times 3, and we get 36 is a least common multiple. Which, of course, when I was making my list of least common multiples, when I was making my list of multiples, I totally missed that. 12, 24, 36, and we had 18 and 36. I was in a hurry, I wasn't paying close attention, and I made a silly mistake. Another reason that I am not a big fan of just making lists of things is because we sometimes overlook things. The less of that we have to do, the less of making big long lists, the less chance we have for error. So a least common multiple of 36, using the upside down cake, prime factorization, 12, 18, 3 times 4, 2 times 2, 3 times 6, 2 times 3, 2 times 2 times 3, 2 times 3 times 3, and it's the same process. These 2's and these 3's are things they have in common, so I only need them once. Bring this 2 in, bring this 3 in, and I've got 4 times 9 for 36. So the factor trees and the upside down cake and the listing out the multiples all get us to the same least common multiple. Of the 3, I find that the upside down cake requires the least work from me. And I am, I like to tell my students, lazy. I can divide both of these by 6. So I've got this times 2 times 3 for 36. All right, taking a look at some activity here with 9 and 12. And I've got 9 and I've got 12, and I can divide them both by 3. So I've got 3 times 3 times 4, 9 times 4, which is 36. I could just as easily do it with factor trees. I've got 3 times 3, and I've got 3 times 2 times 2. So I've got this 3 right here, a pair of 3s. And then I've got a single 3 and a 2 and a 2. 3 times 3 is 9, times 2 is 18, times 2 is 36. All right, 8 and 18. Well, I am pretty sure I can divide both of those by 2. And 4 and 9 don't have any other common factors. So I've got 2 times 4 times 9, 8 times 9, which is 72. All right, 4 and 30. 2 times 2 times 15, 4 times 15, which is 60. $12 and 30. Oh, let's see. Divide those both by 2. Should give me 6 and 15. Divide both of those by 3. So I've got 2 times 3 times 2 times 5. The 2 times 5 will yield a 10. And 2 times 3 will give me a 6. And 6 times 10 is 60. And then we've got 20 and 50. I can divide both of these by 10. And I've got 10 times 2 times 5. 2 times 5 is 10, and 10 times 10 is 100. With each of these, I certainly could have listed multiples and then found items on the list that are the same. However, I find that for finding a least common multiple, the upside down cake seems to work really well. All right, so hot dogs come packed 10 in a package. Hot dog buns come 8 in a package. One of life's great mysteries. Why do we not have the same number of hot dog buns as we do hot dogs? Or why don't we have the same number of hot dogs as we do hot dog buns? So if we want one hot dog for each bun for a picnic with none left over, what is the least amount we need to buy? Now, we're going to have some keywords to let us know that we are looking for a least common multiple. How many packages of each item would we have to buy? So I've got a ratio, and I keep connecting this to ratios. I've got a ratio of 10 to 8, and I would like to scale up so that these numbers become equal with each other, which is kind of a weird way of thinking of it. But we're looking for where things are going to balance out. All right. What is the least amount of each we need to buy? How many packages of each item would we have to buy? All right, so what we're looking for here is a least common multiple, a number at which these two intersect with each other. And then we're asking ourselves, what do I have to multiply each of these by? So slightly different than the equivalent ratios, but we still have a ratio embedded in here. All right, so least common multiple. So if I bought one package, I'd have 10, and I have 20, I'd have 30, I'd have 40, I'd have 50, 60, 70, 80. So that would be the hot dogs. And then we've got the buns, and they are 8, 16, 24, 32, 40, 48, 56, plus 8 more, 64, plus 8 more, 72, plus 8 more, 80. Okay. And I am looking and saying, at what point do these things become equal? Well, I know that they equal out at 80, and I know that they equal out at 40. So it would appear to me that I need 40, there's my 10 to 8, so I would need 4 of the packages of hot dogs, and I would need 5 of the packages of hot dog buns. Now, it's important to recognize that I don't have an equivalent ratio here when I have 40 to 40. But remember, what I'm looking for is where do the numbers intersect. So as I look at my ratio of 10 to 8, I'm asking, what can I multiply these by so that they are the same? What could I multiply 10 by and 8 by so that here I get a ratio of 1 to 1? So we are changing the ratio value here because we want to equal out to a 1 to 1 ratio. And the answer becomes, I'd like to have a 40 to 40 because that is the least common multiple. So I know that I would need 5 packages of the buns and 4 packages of the hot dogs. So a nice connection to our ratio thinking there and extending our thinking a bit. All right, starting at 6 a.m., a bus stops at my street corner every 15 minutes. Also starting at 6 a.m., a taxi cab comes by every 12 minutes. What is the next time both a bus and a taxi are at the corner at the same time? Now, I could certainly make all kinds of tables to organize this. So the bus comes by at 6 o'clock, at 6:15, at 6:30, at 6:45, at 7 o'clock, at 7:15, at 7:30, at 7:45. This is 0 minutes. And here we've had 15 minutes go by. Here's 30, 45, 60, 75, 90, and 105. So I have my multiples of 15 minutes. Now, with a taxi, they come every 12 minutes. So I've got 6 o'clock, 6:12, 6:24, 6:36, 6:48, 7 o'clock. Oh, that sounds familiar. So I've got 12. Oh, we start at 0. 0 minutes have gone by. 12 minutes have gone by. 24 minutes have gone by. 36, 48, and 60 minutes have gone by. So 60 minutes will pass until they are both there again. So the next time they'll both come by is 7 o'clock. Now I could find this, rather than making a big long organized list, I could find this by saying what is the least common multiple of 12 and 15. I can divide them both by 3. 3 times 4 is 12, times 5 is 60. So 60 minutes will go by. 6 a.m. plus 60 minutes is 7 o'clock. 6 a.m. plus 60 minutes is 7 o'clock. 2 gears in a machine are aligned by a mark drawn from the center of one gear to the center of the other. The first gear has 24 teeth, and the second gear has 40 teeth. How many revolutions, how many times will it turn until the marks line up again? So we're asking to scale up here. What is the least common multiple of 24 and 40? When are they going to meet again? Well, I can divide these both by 2, which will give me 12 and 20. And I can divide both of those by 4, which will give me 3 and 5. So I've got 2 times 4 times 3 times 5. 2 times 4 is 8. Times 3 is 24. Times 5 is 120. So they are going to line up again at 120. So I need to take a look at this first gear here and figure out when will this reach 120. When will 24 be at 120? And of course, I just found it right over here. Just by chance, I had multiplied this together and got 24 and found that it takes 5 revolutions to equal 120. Now, if I hadn't done that, I could take 120, divide it by 24, and I would find out that it is 5 revolutions. So after 5 revolutions, they will line up again. All right. Is least common multiple of a pair of numbers ever equal to one of the numbers? Explain with an example. So is the least common multiple ever one of them? So the LCM of A and B, is it ever A or is it ever B? And pause and think about that for a moment and come up with your example. And I'm going to go right back to the example I used for greatest common factor. The least common multiple of 2 and 4. 2 and 4, divide them both by 2. 1 and 2. So I've got 2 times 1 times 2, which is 4. Or I could make my lists. 2, 4, 6. Here's 4, 8. 4 is the least common multiple. Or I could use prime factorization. So is it possible for the least common multiple to equal one of the numbers? Absolutely, positively. Is the least common multiple ever less than both numbers? So if I've got the LCM, the least common multiple of 2 and 4, is it possible to have a least common multiple that is less than both of these? Well, if we stop and think about this for a minute, the answer is obviously no. Because by definition, a multiple is when we have one or more. So we have to be getting bigger. We have to be having more than 2 and more than 4. So, no, we can't be less. So your brain should scream at you when you come to a least common multiple that is less than both of the numbers. You might want to say to yourself, something's wrong here. All right, now, this is kind of our next step in using greatest common factor. We are going to find the greatest common factor of the two numbers, and we are going to rewrite the sum using the distributive property. So we want the greatest common factor of 15 and 9, and we're going to use that to rewrite this. And this is where I really love the upside down cake method, because I've just copied down the 15 plus 9, and I've asked myself, what can I divide both of these by? Well, I can divide them both by 3. 15 divided by 3 is 5, and 9 divided by 3 is 3. And notice the plus sign came down. So I have the greatest common factor, which is 3, and I have 5 plus 3. I have just rewritten 15 plus 9 using the greatest common factor. Which is just beautiful and lovely and easy. And of course, we're looking and saying, well, couldn't we just write that as 3 times 8? Absolutely. But I love seeing the connection between our original addition expression translated to finding a factor and writing it in this distributed form. So for today, for this lesson, I really like to see this, showing that we have the ability to divide the greatest common factor out, or to factor the 15 and the 9. Now another way to think of this is 15 is 3 times 5, and 9 is 3 times 3. So I can divide both of these by 3, which will leave me with a 5 plus a 3. I've divided the 3 out, divided the 3 out. And that leaves me with a 5 plus 3. All right, find the greatest common factor from the two numbers and rewrite the sum using the distributive property. So we want to break things apart here. So I've got 12 plus 18. I know that I can divide both of those by 2, 6 plus 9, and I can divide both of those by 3, 2 plus 3. So I've got 2 times 3, which is 6, multiplied by 2 plus 3. So I've got 6 multiplied by 2 plus 3. And if we carry this out to its mathematical conclusion, I would have 6 times 5, and I would have 30. But the most important thing in my mind for today is to see this right here and to know where that came from and to know how that is used. All right, 42 and 14. These are both even numbers. Divide by 2, 21 and 7. Divide both of those by 7. Oh, need to leave my plus signs in there. All right, 7 times 2 is 14 times 3 plus 1. 14 times 3 plus 1. 14 times 4. And 14 times 4 is 56. Which is, of course, the same as 42 plus 14. All right, 36 plus 27. I see I can divide both of these by 3. And I can divide by 3 again. So I've got 9 times 4 plus 3, which is 9 times 7, which is 63. And 36 plus 27 is 63. All right, 16 plus 72. These are both even. I can divide by 2. 8 plus 36. Looks like I can divide both of these by 4. 8 divided by 4 is 2, and 36 divided by 4 is 9. So I've got 2 times 4, which is 8, multiplied by 2 plus 9. All right, 8 multiplied by 2 plus 9, which is 8, multiplied by 11, which is 88. And if I were to add 16 plus 72, I would get 88. So it's important to notice that as we use this factoring and the distributive property that we're not changing the sum. All we're doing is changing what it looks like. All right, 44 and 33. And changing what it looks like is a horrible way to say that. We are using factors to rewrite each of the terms. Work with them in a different way. Oh, these are both divisible by 11. So I've got 11 times 4 plus 3, which is 11 times 7, which is 77. All right, and we're looking at this in a general form, and we're going to choose any numbers that we would like for n, a, and b. So for n, n, a, b, so we'll pick a 2, and for a we'll pick a 3, and for b we'll pick a 4. So I've got 2 times 3 plus 3, n. N is 2, b is 4. And 2 times 3 is 6 plus 8. And I am testing, is this equal to 2 times 3 plus 4? 2 times 7, which is 14, and 6 plus 8, which is 14. So it worked. So what we're doing on this is we're picking any values we want for n, a, and b, and we are seeing that this distributive property is going to work. And now we're going to test this with subtraction. Now we have to be a little bit careful with the numbers that we pick so that we don't wind up with some negative number stuff, some negative integers. So I'll leave n as 2, and I'm just going to flip-flop the a and the b. So 2 times 4 minus 2 times 3, 8 minus 6, which is 2. And I've got 2 times 4 minus 3. 4 minus 3 is 1. 2 times 1, which is 2. And I got the same value each time. So just a little bit of playing with the general form here. All right, so what can we use GCF and LCM for? Boy, we have lots and lots and lots of options for things that we can use that for. Oh, I was thinking I had something that would appear here. So greatest common factor, we're breaking the numbers apart. We're seeing what do they have in common, which really helped us, as we do our equivalent ratios. We're scaling down there as we find greatest common factor. Least common multiple, we're scaling up, but we're not really scaling up. Well, we're scaling up, but we're trying to find out where are these numbers going to meet, where are they going to intersect with each other, and we saw a wide variety of word problems for both of them. All right, so looking at some ICANN statements here, I can find the greatest common factor of numbers 1 through 100. I can find the least common multiple of numbers 1 through 100. For both of these, we were really looking at kind of a prime factorization approach here as we found what they had in common and worked with that. All right, that would be the exit ticket. So that concludes Module 2, Lesson 18 for greatest common factor and least common multiple. If you've got questions, make sure you talk to your teacher. In the slide materials that are linked to, I've got a lot of resources to look at, different ways to see how to work these kinds of problems. Make sure you complete your problem set.